All right, so let us begin. Okay, cool. So as we mentioned last time, we will start discussing Markov chain, right? Starting this week. And basically with that, we transition to chapter 4 of the textbook, right? And discussing stochastic processes proper, okay? I mean, again, right, not that we have not discussed stochastic processes before, but sort of, right, different aspects preparing us to go into this topic. And so with that said, right, the reason, of course, for the preparation is hopefully you saw that the preparations were not trivial, right? And there are a lot of like advanced materials that you want to master, right? With that said, though, right, what we're going into next will be even denser, okay, and more abstract than what we've been doing before, okay? And so there will be lots of materials, and we'll go over each of them carefully. Like problems will be gone over completely, okay? We won't skip problems like before, just to get to the topics where we want. Right now, we're at the topics that is kind of like the key, right, of the class, the focus. So we're gonna take our time. And so there are a lot of materials, a lot of directions, right? Even though all of them are, for now, right, we'll be only focusing on Markov chain. There are so many aspects that like sometimes it may not be as clear on what we are kind of explaining. If that's the case, right, do ask, okay, that what the topic is, or basically ask more questions, if you will. Like I said, right, just a fair warning that the materials are about to get harder, right? So, all right. So with that said, so right, the focus, right, for this lecture in particular are these 4 topics, okay? But yeah, there will be other aspects later on in the future lectures. So as you will see, right, each of these topic will take time, right, to develop. And well, we may not go over the topic sort of like in sequence or separately because they're kind of blended. So for example, right, the Chapman-Kolmogorov equation here will be discussed fairly soon, while like something like Markov property will show up again and again and again. That kind of discussion will not just be talked about once and then forgotten about, right? Things like that, okay? But kind of roughly what we're discussing right now will be these. One of the important part that we need to focus on is modeling a process as a Markov chain, right? You have seen a bit of modeling, leading up to this topic, as in, well, what do you choose to condition on? What do you view as a stopping time? How do you break down like a random variable as a sum, things like that, right? That's sort of like maybe aspect of modeling. Okay, we're gonna go deeper into that for this lecture. Okay, so well, maybe before we even go into here, right, let me kind of give you an overview of how to think about these things, right? So first of all, right, when you think about stochastic process, basically, right, there are 2 variables in play. One is the randomness represented by omega, right, or the sample space. And then the other one is time, okay? Or this could be infinite, right? So if you have infinite horizon. But so basically, right, it's about something, the word process, right, means that something random evolving in time. And so a visualization, right, would be, so this is time, right, and this is space, right, the value, right? And well, we're gonna just take discrete time just to make it easy. And the easiest, okay, example you can think of for a stochastic process, and that sort of like gives you the motivation on how or why we discuss what we do, our IID sequence. Okay, so like IID coin toss or IID dice throw, right? So why would this be a stochastic process? Well, right, it's random. Okay, so if you watch, right, the value here, right, you could get something like 1 to 6, 1 to 6, right? So this is time 1, time 2, time 3, right? Things like that. Okay, right? So maybe like 1, 4, 5, 2, right? These are the actual, one of the, right, actual numbers that come out. Okay, so that would be, right, something random moving along in time. However, right, why would this be easy, or why would this, right, be talked about, right, in like probability, for example, 477? The reason is, right, the IID here, right, especially the independent, okay, make things simple, right? For example, let's say you want to discuss the behavior of, right, X10, right, the value of the stochastic process at time 10, okay? Clearly, right, if it's IID, well, it's just a dice toss, right? 1 to 6, that is independent of everything that comes before it, right? And does not influence anything that comes after it. It's kind of by its own, right? What's easier, right? I mean, so of course, right, that's not really kind of makes everything easy, because for example, right, it's just easy is in terms of stochastic process, but you can still ask hard questions, right? Depends on, you know, how you phrase a question. For example, you could ask the first time, right? First time to get a 6, right? Of course, this is a geometric, right? First time to get double 6. So first time to get a 6, 6, 4, things like that, right? Again, right, we're repeating, you know, head, tail, that kind of thing, right? That we've been doing with the coin. But right, these are just some, right, some examples to show you that, right, without discussing that stopping time and conditioning, even with an IID sequence, right? The question about stopping time, right, of an IID sequence may not be that easy, right, to begin with. Well, here's another question. What's the probability that, you know, the sequence is always less than or equal to 4 between 1 to 10? Okay. This, right, actually in statistics is related to the idea of order statistics, right? But basically for us here, what it's referring to is what we call a path, right, behavior, right? This is the path of the random variable from time 1 to time 10, right, here. And what we're saying is, right, it must be always below value 4, right, throughout. Notice, right, with the example I'm doing here, right, that's not satisfied because we have a value that is 5, for example, right? Again, this is pretty easy to write down, right? But if you haven't done this kind of problem before, it'll take you maybe, hopefully, right, a couple of minutes, a couple of seconds, right, to think about. All right, but still, right, the IID nature makes things easy, right? You can still pose challenging questions, but still relatively easy. Okay, but so within, right, this picture, right, well, so this picture is really a picture of a stochastic process, all right? But this is like a picture of, let's say, a realized, right, path, a data, if you will, right? Meaning that it has been realized, right? You have seen the values. So the stochastic nature, right, is only shown or it's only modeled behind the scene, right, like that. But now, what would make this like more challenging? Well, you could have the same picture, right? By the way, what we're doing here also has a flavor of discrete time, which, right, we kind of will stay with for most of the class. All right, there's continuous time stochastic process like Brownian motion. We're gonna get to it at the end of the class if we have time, right? And also discrete state space, right? Meaning that the values the random variable can take, right? So time is discrete right here, right? This set is discrete. But the value, right, the random variable can take, right, also discrete, right? So we're not dealing with continuous random variable, right, here, for example, right? So again, discrete just makes things a bit easier to visualize and we don't have to deal with density and all that stuff, right? But anyway, right, if you have a discrete time, discrete state space process, then this picture would sort of serve as a visualization, right, whatever the nature behind the process is. But how do you make this not easy, right? How do you make this, let's say, more interesting? Well, to make it more interesting, right, basically you would throw a dependent structure, okay, into, right, the stochastic framework. Okay. So, right, the reason why it's easy is because if you look at any time, right, you know exactly what it is, right? The random variable at that time, right? A sample at that time, you know exactly what it is. It's independent of the past. It's independent of the future. It is, given. But if you put a dependent structure into these guys, then suddenly, right, things become much more interesting. For example, right, here's a sort of like a simple discussion or simple example, but let's say you have 6 dice, okay, with different distributions, right? Dice 1 to up to 6, right? Okay, I use Roman letter to kind of distinguish it from, right, the values there. But right, basically, let's say you have 6 dice, right? You can color them differently, whatever, right? And they are not fair, right? Because if they're all fair and they're all the same, it'll defeat the purpose. And let's say, right, on throw number 1, right? We can use the same picture even, right? On throw number 1, right? You would choose dice 1, right? So you would choose dice 1, right? And you toss it. But here's the catch, right? This guy is not fair, right? Or right. And then so whatever it comes up, whatever the value that comes up, let's say it comes up value, so here I say 1, right? But let's say it comes up value 2, right? Let's say it comes up value 3, let's say, right? Then you would use dice number 3, okay, for the second toss. And let's say on the second toss it comes up value 4, then you would use dice number 4, right, for the third toss. Basically, right, the value of the toss, right, will decide what dice you would use for the next toss. Does that make sense? Then clearly, right, this will introduce a dependent structure into the sequence of the stochastic process. Does that make sense? Right. So the value, right, or the distribution of the next, right, random variable depends on the outcome, right, of the previous one. I have just described actually a stochastic process to you. A Markov chain to you. All right. Any questions so far? And so, right, go back to the same question. All the questions that we say here, right? For example, the easy question that what is the distribution of x10? Do you see why it's actually much more difficult now to figure out what x10 is, how x10 behave? Can anyone explain, right, in this example, why, if I want to know the distribution of x10, x10 should take value 1 to 6, right, because it's a dice toss. But why would it be much more difficult to figure out what it actually is?
If the 6 die weren't all fair, and there's different probabilities associated to each of the 6 values, then which dice the dependent structure is relevant to us. So the value of x10 depends on which dice is chosen, which is the value of x9, and so on and so forth till you hit the base case, which is the toss x1.
Perfect. That's exactly it, right? The relevant, you just said it perfectly, right? To decide x10, it depends on what you get on x9, and then it depends on what you get in x9, depends on x7, etc., right? All the way, right? Okay. So there, right? Basically, the moment you introduce a dependent structure, right, then even something as small as getting, right, this is called a marginal distribution, right? A marginal distribution would be non-trivial, right? And then just for fun, think about in that setup, answering these questions. And just for fun, answering this question in this setup. All right. This is exactly the whole point of studying the theory of Markov chain, right? For us to get the tool, right, to answer these questions. And by the way, right, let's say a word about the dependent structure here, right? The dependent structure that I just described to you is Markov. Why? And we'll see the slide, right, to make it all more formal. It's Markov because, right, notice that the dependence of x10, right, is on x9, explicitly, right? In other words, if you know what x9 is, then you know what dice you would choose for x10, all right? And then the dependence of x9 only depends on x8, right? But even with that, right, so basically, right, in terms of, let's say, linking the chain, right, step 9 goes to step 10, step 8 goes to step 9, that kind of thing, right? But still, you see that the dependence goes all the way back, right? Like what your friend just said, right? All the way to the beginning, all right? So even though, right? So basically the Markov here only means that the chain link one step at a time, right? The dependence, if you know the previous value, then you know perfectly, right, the distribution of the next one. But that doesn't mean that the dependence stopped there, because, right, the previous value will depend on previous step, etc., etc., etc. Okay. So the moment you build an independent structure, it is throughout. Well, why would this be the easiest? Because you can imagine, right, the dependent structure doesn't have to stay this way, correct? Maybe at some point you want to decide the next one by the maximum of the 2 previous ones, right? Or the absolute difference of the 3 previous ones, whatever, right? You use your imagination. Meaning that, right, basically the rule can change. Who knows? Well, that's crazy, but right, your imagination, right, is kind of like the boundary here, right? You can imagine all kind of structure here. But the point is, right, the moment you throw in dependent structure, things are bound to get difficult. And so the answers, right, to these questions are bound to be much more tedious or much more complex, right? That's what you have to be prepared to deal with. No longer clean answers, one line answer, that kind of thing, right? Long answers, okay? But still, we need to kind of define, right, a very specific or concrete dependent structure so that basically, right, we can operate with it, right? So that's the sort of the big picture, right, of what we're getting into, okay? All right, any question before we continue? Okay. All right, so here, right, we define, right, the word transition probability. And so basically, right, it's about how to go, right, given, you can think of this as a history okay, the history, right, of the process, right? If you know all the values up to the current time, right? how would that determine, right, the distribution, right, the randomness of your next position, all right? And so this, right, as you can see, there are many ways to, so this, in a way, or bluntly, this gives the dependent structure, right? But of course, this is the still quite general. But this is, when you think about it, this is just one way to give the dependent structure among, right, the stochastic, among the random variables of the stochastic process. There are different ways to describe it. But this way, right, has the flavor of time evolution, right? Condition on the past, how would we move randomly, okay, into the future? And of course, right, if all this history or all the previous history, right, can be reduced to the most recent, then it's Markov. All right, as simple as that. But be warned, right? This will get complex quite soon, just with this concept. Right? Any question about the notation or anything like that?
So
yeah, go ahead.
what is the relation between do the EIs make a partition of this state space or
Absolutely
not?
not. Absolutely not. Right. And we just use the E here, but usually, right, the E here just boiled down to a 1 point, right? Like, value 1, value 3, value 5, that kind of thing, right? Does that make sense? Like basically, actually, right? Again, we're being quite abstract here with the discussion, right? This is a history. But if you give EI as a set, meaning, right, let's say go back to this picture, where instead of telling you that it has value 3, I say it has an odd value, it has an even value, that kind of thing. Does it make sense? Then
Right.
actually your history is quite loose. You are not given a very concrete history. That's fine. That's also a dependent structure. Again, right, we are in this sort of thing where we're not really nailing down a structure yet. We're describing a very general possibilities of how things can be described, right? But clearly, the looser your structure, the harder you have the time to deal with, like how to calculate things, right? But to answer your question, right, there's no reason why the EIs have to form a partition, because they actually have not much to do with each other. This is the values, right, or the state that X0 occupy, and then the state that X1 occupy, right? They really, you see, I mean, why would they
Yeah.
have to form,
Thank you.
right? Mhm. Okay. So here we repeat, right, the kind of, the same the same idea as the previous one, with caveat, right? The reason, again, is that as you, let's say, move on from this class, or even have seen, right, all the materials right now, the word Markov is used in, I mean, consistently. It is used consistently. However, like, right, if you kind of stick with like this definition, you will find that the way people use Markov in other contexts is a bit new, or a bit not, doesn't fit into the framework. For example, when I teach math finance, right, we'll discuss like option pricing where Markov property enters, but it's not exactly this kind of Markov we just showed you before. So it's this new one, right? So just to give you all possibilities of thinking about Markov, right? So again, in English, Markov just means the most recent information matters. That's what Markov is in spirit. But to interpret in different contexts, it can mean several slightly different things. For example, here, notice what we just showed you before is sort of like a process of Markov with respect to itself, right? Given its own information, right? How it progresses. But there could be a Markov process that's dependent on another driving process behind it. Complicated, but basically, in math finance, we have Brownian motion, which is like topic at the end of the class if we get to it. And then the Brownian motion itself will drive the stock price. Okay. So we look at the stock price as the process we are interested in. But the filtration or the randomness, okay, that generates it is the Brownian motion filtration. So they are not the same thing, or don't have to be exactly the same thing. However, right, the concept of Markov is still relevant here in this sense that a process is Markov with another, right, generating, okay, information generating process. If, right, condition on the history, this notation, right, the word filtration doesn't have to scare you. It's a sigma, it's a measure theory word that can be precisely defined. For now, really, just really history, right? History of information, but really of the process Y, right? Not X. So basically, given all the history up to time S, all you need to know is the current value at that time. All right, then that's Markov. Now, so same thing, but really now we'll go back to Markov with respect to itself, right? And notice, right, so what is the novelty here compared to the previous slide? Several novelty, right? The first one is, notice the time gap here, right, is n to n plus 1, right? N to n plus 1. The time gap here is s to t, or notice here, m to n, as long as m is less than n. So Markov, right, first of all, should be remembered like that, meaning that the time gap doesn't have to be just the next one, right? So that's why the word is most recent, right? Most recent. So basically, given the history, you can drop all the previous one and just use the most recent one. Anything satisfying that is Markov, okay? And what really is deep, and it's not a graduate class, it's not a super theoretical class, so we won't go into this, but these two definitions actually are equivalent. Meaning that a one step gap and a general gap, as long as the definition is the same, that you can drop the information, right, before the most recent year, then those, either one of them is Markov, meaning that one of them imply the other, right? And the proof, or if you want to really go into the proof of this, you want to have to show that somehow they're equivalent. So that's the first novelty, right? The first generality that you want to pay attention to compared to the previous slide. The second one, right, is, I would say this won't be as relevant in this class so much, that you could have a Markov with respect to some other filtration than the process itself. Meaning that, right, it got generated by another information generating process. And so it's Markov with respect to another process, not itself. But most of the time, we will deal with Markov with respect to the same process, okay? So meaning that when you condition its own history. You don't condition on the history of another process, right? The last is, we notice we use the language of conditional expectation here, while we use the language of probability here. As you will see, right, or I think I didn't harp on this too much this time, but expectation and probability actually are equivalent in this way, that if you look at expectation of the indicator function of a event, that's a probability that the event happens. Right? Why? This is exactly the Bernoulli, right, idea. If you have an indicator random variable, right, then expectation of the indicator random variable is probability of by success, meaning probably that the event happens. So the last part here, you don't have to pay attention too much. When you come to a concrete case, you always realize that it's true. But right, the gap, right, the gap that doesn't have to be exactly one is something I think is really the message here. The others, right, are FYI, meaning that you should be aware of it just in case you read something in some more general context. Any question about these two slides? Okay. Okay. So this again, right? Just sort of giving you some intuition. I think I've talked enough on, so I'll just pause here for maybe a couple seconds, and we'll continue. Right? If you have any question, ask. If not, we'll continue. All right. So here, right, is the example of, let's say, I don't want to say most simple, right, Markov process, Markov chain, Markov process, but basically, right, it will random walk, right, will show up as an example for us throughout, right, this chapter. So notice, right, so several things. When you have a process, right, like this is a process, right, namely the S. Again, right, why? If you're not used to this, it's kind of helpful for you to kind of ask, why is it a process? Again, the reason is very simple. It's a random variable. I mean, it has randomness, right, represented in kind of the random movement, and it's indexed by time, right? As time moves on, you have a different random variable. So that's why it's a process, right? But when you have a process, right, notice when you claim something is Markov, you need to kind of prove it. All right. And we'll get involved with this aspect a little bit in this lecture and the problem set, meaning that we will, right, look at things that may be Markov, may not be Markov, and explain why. The proof code, right, that we'll be doing will not be as involved as this. Okay. Or technically speaking, if you want to write down a mathematical proof, you might have to use this kind of language. But, right, like I said, we're not requiring you there. Just to show you, right? Basically, the idea that you don't go walk in and you say, "Oh, that's Markov, right? That's not. You have to establish it somehow. And if you want to establish beyond any doubt or whatever, right? Mathematical symbols what you use. But we're not gonna do it that far, right? We will kind of show you the idea of Markov and explain it, right? But anyway, so how do you prove, right? Something is prove that the random walk is Markov. Well, right, you condition. And by the way, right, when we say something is Markov without any reference, so by default is with reference to itself. I can't find today. By default, with respect to itself, right? If we say Markov, okay, that's why we condition on S. Notice, right here, you already see the phenomenon of a possible other filtration that you can condition on, namely what? Namely, right, the X here, right? The X here generate, right, the position of S, isn't it? So instead of condition on S0 to SM, you could condition X0 to XM. All right, so you can talk about, is it Markov with respect to the X's? We'll look at that, right? That's an interesting thing to look at to kind of pick your kind of curiosity or kind of start a discussion. Here we'll condition on, right, the S's. Again, right, so the simplest example you can think of, right, is the 1D random walk, where let's say you start at 0, right, and you have a coin toss, right, and if it's P, you go to the right with probability, right, you go one step to the right, and you go one step to the left, right, with possibility 1 minus P, right, and you keep repeating, right, things like that. I think most people have seen this example. And right, you see that this example that we're writing here exactly is the random walk, right, where xi are IID with 1, right, with probability P and minus 1, right, with probability 1 minus P, right? So random walk in general is like that, where the X now, right, is a step size. You don't have to step 1 minus 1, right? You can step with other possibilities. So the S here, right, represents the position, right, of the random walk at those times. And so if you condition, right, on these, notice, right, the technique is if you condition on this, you know what it is, right? And then here you add the future movement. This is the future displacement, right? Counting from time m, right? This is very common. This is a very common technique, right? To analyze the dependence of past to future, you use the past and you add on, right, the change from past to future, right? And then, right, notice that this SM is known from the past, so it can come out, right? This is a given knowledge, right, from the past history, so it comes out as a number. The XIs are independent of the past because, right, this is a movement from time m+1 and so on. So that's why it comes out as an expectation. And I think, oh, well, and then this is just a number, right? This is just a number. So you can repeat the same process now with this, and then you'll get the same expression. So this is that's kind of like a shortcut there, right? But if you repeat the same calculation, same history, same argument, you'll get this. That's why these are equal. And that's why it's Markov. Okay. Any question here? All right. So yeah, go ahead.
How did you go from how did you go to the last equation? So I understand SM comes out as a constant, have the expectation.
No, right, correct. But the way you read it is not like that. That's why I say it's a shortcut. I mean, it's a slide. That's why. So you stop here, kind of, right?
Okay.
And then you repeat the same process with this guy, plugging it up here. And you can see that, right, nothing really changed in the argument. Because why? Notice you only use SM here in this argument, you see? You don't use the whole history. That's actually the trick. So you do this once, stop here, you do it again, and then stop there. And then you conclude they're the same. Makes sense? You don't go down, but you kind of repeat with the, yeah. You see
next time you do SM -1. And
no, then you repeat the same calculation here with SM like that. Forget that for now. Right, now you repeat this.
Okay. Oh,
you see,
okay.
All arguments, right, follow exactly the same. Right? Why? Because the only thing you use is SM, right? That's why. By the way, this is exactly the intuitive reason why random walk is Markov. To figure out the future position, you only need the current position. You don't need to know where you were before this current position, right? Because the future steps are independent of the past. And this proof spelled it out with the SM used in the conditioning. Does that make sense?
Yeah, thank you.
Mm-hmm. Any other question before we continue? Now, let's kind of to show you, right, why Markov is not a simple concept. Let's repeat, right, this idea, meaning that is the random walk Markov with respect to the x's. What if I look at this? What do you think? Is the random walk SK, SM, whatever, Markov with respect to the step size? Yes or no? So notice, right? Exactly, you will encounter this. We will encounter these kind of questions going through the problem set or going through this lecture, or you will encounter this in real life or in other courses, right? It's same story with independence. People would love to say, oh, that's independent and move on, move on, move on. Never even question it because someone told them this independent. Same thing with Markov. Many things are Markov, so you're told it's Markov. You never even bother to question. But when you have to really establish something yourself, or you have to check someone's work, right? Thinking on why something's Markov, or even right harder, why something is not Markov, right? Is a big deal, or even not a big deal. It's a real deal. Is when you really have to show your understanding there. Is a random walk Markov with respect to a step size, no respect to itself, right? Again, what could I mean by this? Well, what I meant is very simple, right? Can I drop the dependence, meaning that is it equal to this? Any suggestion?
Is the reason you wouldn't be able to if S and M are dependent? I mean, S and X?
So no, right? That so wouldn't be able to is correct, but the reason you give is not convincing. Why? Because notice that S and S here are dependent too, right? That's the whole point, isn't it? Markov chain, we have dependence everywhere. So dependence is not really the point. It's about information, right? So notice Markov, you have dependence anyway, right? You will have dependence anyway, right? The only time when you don't have dependence is when you have IID sequence. By the way, that's called white noise, okay? In some circle. The white noise might have some more special structure, but roughly speaking, you could call something IID white noise. And what that means is really, there's no information there. It's very easy. The moment you throw a dependent structure in, right, then things are bound to get complex. Also, that's the simple message. But, right, the information dependence is a different question, right? How that dependence is shaped is a different question. And the simplest way, right, quote, simplest, is to make the dependence not on the entire history, but on the most recent state. Okay? That's the simplest dependent structure you can build in. And you can see intuitively why, right? Because right? If you depend on the whole history, that's bound to get complex when you calculate things. So you have to track, right? Just think about tracking information. You have to keep track of the whole history to move forward. Well, all you have to do is just keep track of the most recent state and move forward, right? And if you do coding, things like that, you know what I mean, right? Instead of keeping the whole stack, you only have to keep the most recent value on the stack, right? Things like that. So, right, but to emphasize, right, that's about information, right, dependence, and it's not really about dependence as an abstract concept. So you have to really look into the meaning of these things, right? And that's why it's hard. You cannot just swing a generic formula and say, well, it's this, so that's why it's not Markov. No, it really depends on each problem and the meaning of each. Any other suggestion? So the answer is no, right? But the reason, okay, is more along this line. The reason is, right, based on a kind of like a rule. I'm not sure if I would put it somewhere here. I think I put it somewhere down there, maybe. But basically, something is Markov with respect to something else if given whatever the information, right, you need to be able to completely determine the behavior of the future state. Okay. So emphasis on completely. Like this, right? first of all, notice if I have the whole sequence, right, of x0 to xm, notice, right, in effect, what am I given? I'm given Sm, isn't it? In fact, right, these informations are equivalent. Knowing x0 to xm is the same as knowing s0 to sm, because that's a first important recognition. You understand? Right? Because from the x, you can reconstruct the s, and from the s, you can reconstruct the x. They're really like integral and derivative. You know the derivative, you know the integral. You know integral, you know the derivative. Okay, so far?
Yeah.
But now so basically, given this, you actually know the most recent information, therefore you can determine where you go next. But if you drop all the steps and you can only keep the most recent step, do you know where you are right now? You don't, right? You only know how far. It's like, right, it's very simple. In this language, let's say at S10, I only tell you that previously I stepped one step to the left. That's it. Is that enough for you to reconstruct the future, to construct the future, or reconstruct where you are?
No.
No, right? In fact, right, this is really nothing, right? You cannot really do anything here. So notice that basically, right, right, this and that are equivalent in deciding the future. But this and that are not equivalent to deciding the future. That's why this is not Markov with respect to the x. Do we understand? So again, right, the reasoning here can only be done as best as that, no more, right? Because, you know, unless you want me to throw in a lot of math at you, right? This is it. But the thing is actually better that way, right? The intuitive reason on, you know, what information is enough to decide the future and what information is not enough to decide the future. If you think about the context, if you think of the problem, it should be clear to you which is which. Okay, any question about this? And right, you can point out to something concrete too. It's not just waving hand, that this and that are equivalent. Therefore, this implies that. It implies that. Well, this, right, is clearly not even equivalent to this, right? Therefore, this is very, very little information to decide Sn. So you can point that out concretely. Okay, any question about this? Okay. So, yeah, right. So now, well, so here, right, going forward with this kind of slides, just a fair warning, you might see a repetition-ish, okay, of information of slides, that kind of thing. Well, we have said something like this before, right? The reason, and I choose to do so, not because, you know, I'm kind of senile, I might be senile, and then forget what I said before, but more like these are so important, I want to repeat it again and again, so you see it and it gets into your mind, okay? Or, you know, with slides, right, things are bound to be forgetful, right? Forget it once you go down the lecture, so I want to repeat something just to kind of refresh our memory, okay? But yeah, right, same thing here, talking about Markov chain. So, but kind of, you know, throw in more like, you know, I guess there was a question on the EI kind of thing. Right now we get concrete into the states, right? And then we call this, because they're discrete, right? Okay, so it's not an interval, right? It's just concrete values. And so the dropping of this, right, is called Markov. But notice, right, that's not enough yet. Because notice, implicitly here, there's still a dependence on n. Right? Meaning that, yes, to know where you go next, you only, right, need to know the current state. But for example, let's go back to the random walk example here. it's like suppose you're at S10, right? Then at time 10, you still move left and right, but the coin you use depends on what time it is. Does that make sense? So, well, there's a, yeah. So what the coin you use, right? It's not random. Let's say the coin you use, the probability of success is going to be Pn, right? Where Pn is, let's say 1 over n. I'm not sure. I'm just making up numbers, right? So in this sense, right, notice that a random walk where, right, the left and right transition probability will move, right, with time. That's still Markov, think of it, right? Because to know the future position, I only need to know the current position. The coin toss is still independent, right? But what happens is the movement into the future will not be homogeneous, right? It depends on how far into the future you're moving. Obviously, again, right, those kind of things just make things more complex. But again, more complex doesn't mean not possible. In fact, more complex might mean richer model, maybe fit the reality better, right? But to make things simpler, or right, the classical state, the classical setup is to consider things not dependent on n, right? So eventually we'll just drop it down like that. Meaning, right, notice the transition probability only depends on where you are now, and then, right, where you want to be next. This is one step, okay? This is one step transition probability. We'll talk about multi-step soon, right? But it's purely spatially dependent. No time involved. No time meaning like depend on where you are, when, right now. Right? Notice that time gap matters. N to n plus 1 matters, but the n doesn't matter. That's what we mean. Okay, so far? All right, any question? All right, so let's give you a quiz, all right? The quiz here will just be sort of abstract. So define, right? The Markov property. You know, as best as you can. Right, use mathematical equation. All right, cool. Any question before we take a 10-minute break? All right, so we'll continue at 10:35, okay? Okay. Any question before we continue?
For this definition, were you expecting the filtration definition or the very beginning one?
Yeah, so that's why I say as best as you can, right? So the very beginning one would be the one that is with respect to itself, while the filtration one, if you refer to the Y, is with respect to some other process, right? So technically speaking, the filtration one is more general because when we say a Y can be also X itself, right? Does that make sense? So,
That
but I'm not really being rigorous on this. We'll be rigorous on problems on homework and things like that. Does it make sense? But like I said, I mean, if we were to go into this rigorously, we'll do a bunch of math calculations that I think is not really right. I mean, helpful at this stage. Does that make sense? So some understanding is good enough here.
Okay, thank you.
All right. So to recap, right, the Markov chain we'll be dealing with will be, right, time independence, time homogeneous, right, and Markov. So this is, right, and of course, right, because Pij, right, Pij looks, let's say, right, temptingly like a matrix notation. It is, right, it's a transition matrix. All right, and I think this is not first time you see this thing, right, or heard of this thing. So if a state space has n elements, right, if X can take n possibilities, right, then Pij, right, well, you arrange it, right, let's say a 3x3, right, and here's the thing, how to say this, the notation, right, there's no reason why you have to start a state at 0, right? For example, let's say a dice toss, right? Dice toss is 1 to 6, for example. But conventionally, if you have no, or at least with the textbook, right? If you have no reasons not do so, sort of like they start at state 0, right? But I might deviate from this. I'm not so sure. I think I try to stay with this. Same, right? Time, they also start time at 0. So k equal to 0 is start time. Again, these are convention. There's no reason why you're gonna start at time 1 or some other time, but so anyway, right? So let's say if n equals to 3, right, is this. Now, here's the thing, right? Very important. The row sum is 1, right? Oh, by the way, entries are non-negative, right? That's obvious because the entries are the probabilities. But the row sums is 1, right? Not column sum, okay? This probably is an elementary mistake. Hopefully you won't make it, but row sum is 1. Why? Because again, notice this is a transition from I to J, right? From I, right? So this is not symmetric, meaning Ij and Ji don't take the same meaning, okay? Because of the flow of time, right? So you flow from I to J is potentially different, right? If you flow from J to I, and if you flow from J to I, you're really talking about this J and this I right here, okay? So that's why, right, if you sum over all J, it is 1. Why? Because fixing, right, a current state, right? Fixing a current state. Sorry, let me just do a dot here, right, to make it clear for you. Right, and then this, right? So like that, fixing the current state, and you look at all possible future states you're gonna go into, right? Then that's 1. So here's the thing, right? Basically, this is exactly coming from once upon a time we discussed condition F is a probability. This is probably lecture 1. That exactly is where like is relevant right now, okay? So for example, let's say you throw in things like 0.5, 0.4, 0.1, 0, 0.4, 0.6, 0.5, 0, 0.5, right? Something like that, okay? So yeah, not necessarily symmetric. Notice, right? It's not symmetric. We'll talk about this later. But or soon, right? Let's just kind of like clear this up too. Is there any rule about the column sum? Like column sum has to be 1, column sum has to be less than 1, column sum has to be bigger than 1. Any rule about column sum in a transition matrix? Or is there any structure about the column at all for a transition matrix? Any meaning?
I don't think there's any meaning, but trivially, for any jth column, the sum of all the probabilities has to be less than the number of rows.
Yeah, because each
That's very
entry
trivial.
is each entry is bounded by 1. So right,
Yeah,
trivially, right? That, but that
but I
would
can't
not
think
be
of
right.
anything more interesting.
No, right, true. No, good. In fact, right, what I'm referring to is some people might think that the column sum must be 1, less than 1, bigger than 1, whatever. Right. In fact, no. Right here, for example, this column sum up to 1.2, 0.8, right? That. So right, no rule. In fact, right, what if you were to sum, right, the column sum? What are you looking at? You're looking at that. So you're looking at, right, you're right now, you're in your future state, you're at J, right? So for example, you sum over here. The future, you're in state 1, and you sum over all transition probability into that state, right, from the previous possibilities. Okay, yeah, you can sum that. What does that mean, right? That's not a logical statement in the sense that doesn't give you anything like a totality or anything like that. All right. So that's what you're doing right here. You're summing with changing on this one. But notice also this is weird because, right, as we mentioned, with conditioning, you fix what you're conditioning, right? And you move this again, right? It has that taste. All right. So now, right, any question? Let us kind of maybe look at, let's say, something like this. Okay, hopefully it works. All right, so what's special about this Markov chain that I just wrote? Again, right, we're not gonna see so many of these things, but just see if we can read this, right? What does this mean?
For states 0 and 1, you deterministically transition to state 2 and 1 respectively. It's not probabilistic.
Right, so correct, right? So if you're at state 0, you will always go to state 2, right? And by the way, right, there's this idea of graph, right? Drawn directly really from graph theory, right? So there is some connection to graph theory here. I think we call this transition matrix here, I think, is it called adjacent matrix? God, it's been a while. But in graph theory, right, there is a matrix that's very similar to us that represents, right, here. So we have numbers here, but a lot of time they have 1 and 0. So representing connection is called an edge connection adjacency matrix or something. But it can also be a number, which means the weight, right, between the nodes. So in graph theory, these are considered nodes. These are the strength of the edge. So this is a directed graph, right? That graph. Again, I'm making this connection for those who have done like graph theory, things like that. Not that you need it here, but the representation could be helpful, at least a starting point, if you haven't done this so far. Something like this, right? And 2 goes to 0 with probably 0.5. 2 go to 1 with probably 0.5, right? Things like that. Helpful as in like you can visualize small Markov chain, 3, 4 states, obviously, right? Not going to be helpful 100 states, not helpful with abstract results, things like that. But it could give you some visualization, right? And people do this too. So it's a nice tool to have along, right? But yeah, right. So 0 always goes to 2. 2 can go back to 0 and 1, right? With some probabilities. 1 here, right, is what we call absorbing. meaning that once you go into one, you're stuck there, right? You're not gonna escape from one, okay? But I'm doing this so just so you see, right? Here, this doesn't indicate any absorbing, right? 0 goes to 1 deterministically, but there's no absorbing behavior. It's the diagonal entry, right? That indicates absorption, at least for that current that state. Okay, so far. Okay, yeah. So right again, just indicating that, right? So this is sort of like the abstract representation you see in the textbook. So with an infinite, right, state space. Okay, what is an infinite state space? Oh, by the way, right? So I think an implication here, right, is finite, right, state space. So there is that, right, distinction that will be relevant to us at some points, that we can consider a Markov chain with finite state space or infinite state space, right? So finite state space, right? Easy, like something like dice toss or something that's dependent. Infinite state space, what would that be? Well, a random walk, right? On one dimension would be infinite state space, for example, because right, the random walk can kind of travel on forever, right? At least with some probability, right, to the right and to the left, things like that, right? So it's infinite state space. So we still, right, can make sense of something called a transition matrix, right? And possibly, well, there's functional analysis, but I think I'm not sure if folks do define an infinite dimensional matrix exactly formally. Maybe I haven't done linear algebra in that advanced. I haven't taught it, so I don't. It can be done, right? Anyway, but so we still call it, right, a transition matrix. That's all, right? So just so you know, weirded out by that. It's a computational convenience, right? Can still apply, right? But you have to do it with care because there's some convergence issue and whatnot, right? Okay, but usually when it comes to infinite state space, we kind of write down explicitly as an infinite sum. We don't use matrix notation as much, but we could at some point. Okay, yeah, right. So we talked about this so much. Not gonna repeat, right? All right. So this, right, is a let's say example 101, right? People always give this example as baby, right? Introduction to Markov chain, right? So whether it's going to rain or shine today depends on whether it has rain or shine the previous day, right? And alpha, beta, that kind of thing. And you write down the transition probability. Notice there's something here that you need to do, meaning encoding, right? The information into a state. And by the way, right, this is not trivial, as you will see immediately on the next slide or so. But that's actually the aspect of modeling that I'm talking about, or I referred to at the beginning, right? That basically, with a Markov chain, when you're given a word problem, which is a favorite thing we do here in this class, right? You have to encode, right? Not you have to, but yeah, you do encode things into mathematical symbol, right? And so with Markov chain, besides the explicit probability given whatnot, right? You have to encode, okay, things into a state, and that's the annoying thing ish, because right, the information you have to kind of remember. Okay, we call state 1 if it rains, things like that, right? But right, and it has consequences. You'll see, right? But hopefully, you see that this is obviously Markov, right? When I say obviously question mark, I don't mean it's not obvious, but just pause a little bit, right, to see if it's truly obvious, and if someone really press you, you can explain it. Because as you will see, right, we'll go to the next problem where it's not obvious. Any question? Okay. All right, we'll go back to this. Yeah. So, right, we'll go back to Chapman-Komorow, but just to kind of continue the discussion right here. So basically, this kind of slides, right? Like I said, the topics may not move in a linear fashion. This is along the line of what I call modeling a Markov chain, right? Markov chain now just called MC, right? Too. So you can see, right, with the description that basically the state, right, of the weather does not just depend on the previous day, yesterday, but it depends on the 2 previous days. Okay, so like this, right, so on. So here's the thing. Let's put it bluntly. Is this a Markov chain? Let me ask that question. Is this a Markov chain? What do you think?
I would say yes.
Reason?
It's still conditioned on the most recent history, right? Because there's a finite number of directly previous states. So the rain on the I
Interesting.
position is conditioned on the rain on the I-1th and I-2. Like I think you can still recover a recurrence relation, is my logic.
Okay, let's hold on to that thought, right? Any other suggestion? Any other suggestion on whether or not this is a Markov chain? All right. So let me play the innocent bystander here, right? And when you said, right, not that what you said is wrong or whatever, when you say, well, it still depends on the most recent history, right? An innocent bystander, which maybe some student here in this class even haven't seen all the previous slides, will ask, wait a minute, how can that be? Because the most recent information would be only yesterday, correct? While here you say it extends on the day before as well. How can you say that it depends on the most recent history? Is that a reasonable question? How will you answer that?
You could make it precise with some sort of delta, but I think it's that there's a finite number of previous states. It's not like I'm saying the entire history, but I'm saying only 2, only 3, only 5, and then
No. You are getting to good points, and you hit all on the right notes. I would agree, right? So let me let me pause, right? Any other suggestion or input before I kind of explain this? All right. So first of all, when I say the word, is this a Markov chain? The first thing you have to say is that's an ambiguous question. I mean, what do you mean by this? Right? What do we mean by this? And again, tangential, but students are usually annoyed when they bring this kind of question to me and they ask, is this? I'm like, what do you mean by this? Right? Because you see, that actually is the confusion here. When I say, right, and I know when I say this, okay, this is an intentional question. Is this a Markov chain? I haven't spelled out what I mean. And you have to understand that this is a lesson here. You cannot resolve whether something is a Markov chain until you define it. Understand? Meaning you have to encode it. You have to encode the state space. You have to encode things. Then we can ask questions. Before that, if we both understand what this means, fine, right? We can go past that. But a lot of times with complex question, we can't. All right, and you understand why, right? Again, right, without kind of repeating myself, but students don't like to, do this because, right, it takes so much time, right? So they just say this and expecting the opposite understand what they mean. But no, right? How can we understand what you mean? So the word this here, right, is ambiguous. So let's say this, right? Can we repeat the previous one where we denote, I think, 0 as rain, right? And 1 as sunshine, right? Not rain, that kind of thing. So, right, when we say xk, right, is 1 or 0, right? Xk's track the weather on day k. All right, now I'm clear on this, right? I have the encode my state space. Then this process, all right, I'm not calling it a Markov chain or not. I'm just calling it a stochastic process, which is true, that track the weather on each day. Is this a Markov chain? Now, right, my question is correct, precise. Now we can ask again, is this a Markov chain? And what should the answer be? Well, can we decide this question? Can we decide this question?
No, we would also need k minus 1.
Exactly, right? That's the point. And so you see, in this sense, is not Markov, completely not Markov. All right. So in this sense, that's the pushback question. Now, put very clearly in mathematical symbol, right? Okay, any question here? However, right, there is a lot of truth, a lot of good truth, if that's even a word, in what you said, right, in what your friend just said, that somehow this can still be salvaged, this can still be rescued, and blah, blah, blah. And there's a word finite history, right there. What do we mean by this, and how can we make that precise? Any suggestion? Okay. So what we mean by this, right, or how we make this precise, is exactly in the encoding step, right? In that part where I emphasize the word modeling, right? And again, you'll see that this will come back to haunt us again and again, haunt, or whatever, right? Good stuff. Because how you model something exactly affects how you see it, how you work on it, etc. Now, for something simple like this, well, that's the only way, right, to encode information. Meaning, right, you let 0 is rain, 1 is not rain. However, in a, let's say, more complex situation like this, well, is it, again, this is exactly why we get stuck, right? It's so obvious we just want to call it rain, not rain. But is that the only way we can encode information? Can't we, let's say, enrich our state space? Can't we encode more information as we go along? Is that a possibility? So this is, let's say, too little, right? Can we enrich our information? Can we encode more? The answer is yes, we can. How? And the answer actually is almost obvious, but if you haven't seen it, right, it would sound like, earth-shattering. We can encode sorry, was there a suggestion there? We can encode the weather of 2 days at a time. Okay, because why not? We can, right, encode. The modeling part is almost like it contains a lot of freedom. You can encode a lot of things in a lot of ways, and smart encoding, right, intelligent encoding is exactly, or smart modeling is exactly the key to, let's say, success, right? That is super hard to formulate. But here, for example, I could encode 4 states, where it's rain, 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 shine, shine, rain, shine, shine. All right, because clearly, like, somehow we are carrying things, 2 stay at a time, right? Because so let's see if we could do that. And notice, just because we come up with a clever idea, that doesn't mean it may work. All right. I'm not saying that whenever you hit on a bright idea, it must work. You have to check it, right? You have to check. You have to clearly establish that it works. So let's carry this out, right? And see if, and what's the let's say the mark, right, that will determine whether it works or not. Well, it will be, right? Oh, wait, how come? It did not copy. All right, cool. Right. So the mark that whether we are successful or not, right, will be based on how we can do the transition. But for example, right, if we do this, then we need to be able to do something like this, etc. For all, right? Let's say ij, right? This is I, this is j. Understand? Meaning that we can write down the transition matrix. If we can, our encoding is successful. That's Markov. If we can, that means our encoding is not successful. But the catch is you may not be able to tell if there's no successful attempt, right? You have to prove that. To prove a negative is always harder than to prove a positive, okay? But anyway, right, let us write down the transition matrix here, or try to write down, right, and see if we can. And this is, again, right, an exercise for all of you to try, okay? Because writing down the transition matrix, as tedious as it is, will be a required step for this lecture, for this chapter. If you can't write it down, then whatever you want to do next is irrelevant, right? Okay, so let's try. Anyone wants to read out the first row to me? And make it easy for you, right? What are these 2 entries? I claim that these 2 entries are zeros. Do you see why? What do I mean by this, right? To go from 0 to 2, I have to go from rain to shine rain, right? What do I mean by that? Or if it's not clear what I mean by that, do we understand what we mean by this?
The second R has to be equal to the first whatever letter, right?
Right, because this is day before, yesterday, today, right? That's what we're encoding. Does it make sense? We're encoding 2 days at a time, right? Correct? So that's why, right? If these two clash, that cannot be. Does that make sense? That's the meaning of our encoding, or if I went too quick on that, you should ask. But is that clear now? So that's why these are zeros. What about these two? The information is given here, okay? What's 0, 0?
It's
means-
0.7 and 0.4.
Nope. I don't even have to like look at the information. I know that you're
Oh
wrong.
wait, it doesn't add up to 1. Sorry.
Correct. So must be, this must be,
0.3.
yeah, right? Is it in the table? Or
But
is
it's
it in
not.
here? It's not, but you don't have to, right? Because if it rains past 2 days, then it will not rain with probability 0.3,
Oh,
right? It
sure.
must be
I'll do
induced.
it.
Okay. All right. So can we do the row 1? Tell me the entries. What is row 1? What can this not go into?
It's 0, 0 for the first 2 columns.
2 entries, yeah, correct.
Oh, sorry, yeah.
Okay, good. No, don't worry. Yeah, I understand what you mean. Okay. Then the next one will be
0.4, 0.6.
0.4 and 0.6. Thank you. Do we agree? Do we agree it's 0.4, 0.6? You have to pay attention here, right? I'm not gonna approve or not approve without you thinking about it too. Do
Yeah.
we agree? Good. All right. So I'll let the class run this, okay? What about the second row? I mean the third row, right? The second entry, whatever. Can you read it to me?
I would guess 0.6, 0.4, 0, 0.
Is it?
I had that it was
Yeah, go ahead.
I had that it was 0.5, 0.5.
Yeah, I don't think the 0.6, 0.4 would repeat. Yeah, this sounds more reasonable. What do we think? Is 0.5, 0.5 okay or no?
I have it for
Do we
row.
agree? Yeah, good.
I was just gonna say I got the 0.5 for row 2, column 0, which
Yep.
is probability of it raining based on the fact that it didn't rain yesterday, but it did today, which the chart
Yeah,
said.
so that, which is SR, correct. No,
So
I agree.
Okay.
Yep, I would agree. Correct. That's a good interpretation. Good. All right. Last row. Three cannot go to 0, right? 3 cannot go to 1. So if it does not rain on either day, it will rain tomorrow, right? With probability 0.2, so SR. So that's 0.2 and 0.8. Do we agree? Any question?
Could you just explain how you got entry 20, the 0.5?
Sure. So 2, right, is SR. So which one are we looking at? Today it rains, and yesterday it did not rain.
Oh,
we
okay.
isn't it? So the word S here just is our complement, right? Again, it's a encoding, but is that
Never
okay?
mind. I got confused with the time. Okay, yeah.
No, right. And this again, right, is also a possibility. This is my notation and is possible, right? That's understandable that you don't understand what's going on in my mind. But that's why we have to have questions. And I did say, right, there are a lot of things here. But right, I'm not saying that I'm doing everything obvious, anything here. But I think, right, it's sort of like in the sequence that we read left to right. So this kind of is today, this is yesterday, right? But of course, if you want to make it super clear to people, you can do something like that, etc., etc. Absolutely, right. All right. Any other question? Okay. So, right, notice, right? So again, this example illustrates a lot of things. Of course, the first and foremost idea is, right, that depending on how you encode the information, you can have a chain to be Markov or not, right? So notice that both of these, the one that tracks only one day and the one that tracks 2 days at a time, both track the same phenomenon. They're not the same chain. They're not the same process, right? Okay, we call it X whatever, but one is X, one is Y. They're not the same chain. All right, but they top of the same phenomenon. Let's put it that way, right? So for the same phenomenon, you can encode things differently to arrive at a Markov chain or not. But that will make you noodle, right? From now on in this chapter or for the rest of your life, who knows? But that's again why modeling is important. Second, right? A less obvious point, but maybe there is, depending on how you encode the information, you might get a different matrix, right? And I think here we got a different matrix than the one we wrote down, because I think the encoding here is not the same. All right. But so does that mean that one's right, one's wrong? Absolutely not. Both are right, right? It's just how you model things, right? And so here is again where you have to pay extra attention to what's, given, and as long as the information is consistent, that's fine, right? But if you are not restrict on like what state is and you come up with the state yourself, you have 4 factorial ways, right, to do things. And third, right, it's helpful, right, to define things kind of clearly so that there's no doubt on what we mean by stuff like that. But when I was explaining words, maybe I cut through a few steps. But right, so okay, any question? So by enlarging, right, the history or enlarging the information we encode, we can still have a Markov chain. So, or the lesson here is Markov or not is also a function of modeling, meaning that, of course, it's not boundless, meaning that you can just always define something as Markov. There is a limit to that, right? That you cannot carry this forever and things like that. But where is a hard limit? Think about that, right? That's not, trivial, right? But think about it. Is there a case when we have to say no amount of modeling make this not Markov, right? We'll try to address that a little bit. Okay. Okay. Any question? Okay. So now let's go back to a very important topic of Chapman-Kolmogorov. All right. So, right. So let's say a easy motivation, right, for Chapman-Kolmogorov is, okay, notice that P is a one-step transition, right? P is a one-step transition matrix, right? It tells you how to go from one state to the next, right? But, well, the obvious question is, can I do 2 steps? The answer must be yes, right? Otherwise, right, Or let me just say this, right? I mean, let me remark on the answer must be yes. Basically, any sufficient description to a stochastic process and Thomas stochastic process in general, as you will see, right, a theme that you have to watch out for in this course and later on in your career is that there are many, many ways to define a stochastic process, right? I think I touched on this theme on lectures 2 or 3, whatever, right? You can define as a sum, you can define as conditional probability, you can define as like increments. But whichever way you choose to define it, it must completely characterize the stochastic process, meaning that it must whatever your description is, it must allow you to compute all things you want to compute about the stochastic process. If there's certain computation you want to do, but it's not derivable from the definition, right? Of course, taking away the fact that you're not smart enough to derive it. But suppose that you can prove that computationally there's not enough information. That means your description of the chain is not complete. So if we accept the fact that the Markov chain description with the transition matrix that we have done is complete, which is kind of based on faith-ish, right? And what we're doing here is sort of like verifying that. Then, right, you must be able to do more general things than just one-step transition matrix. Okay, one-step transition probability, like 2 steps. Okay, and right, I think I kind of give the secret away, but this is a law of total probability, right? But it's really the law of conditional version, right? Remember that one? Where, right, it goes like this, right? Let me tell you. So the law of total probability conditional version says P of E given F is P of E given FG times P of G complement, G given F plus P of E given FG complement times P of G complement given F, right? So this is only a 2-set version. Here we have like an n-set version, but I'll show you, right? Let's see if I have a proof here. Okay, I don't. I'll show you. But basically, right, that basically here the point is to want to add the extra information in, right? You want to add the extra information in as represented by G. So you have to pay it back. But you pay it back by conditional because what you had originally is a conditional probability. Okay, so let me show you how this works. So what I want, right, is P xk plus 2 is equal to J given xk equals to I, let's say, right? So obviously I want to insert, right, the information on xk plus 1, right? I want to insert that on, correct? And so I have to pay it back by multiply the conditional probability. All right, and I have to sum over all the dot. Okay, so far, that's the law of total probability conditional version. Now the dot looks mysterious, so I just throw n in it, sum over all n in state space. Okay. Now, right, clearly this is P I n, right, going from I to n in one step. How about this? Well, I'm glad you asked. Notice this is a 2-step dependence, but by Markov, I can cross away the not recent one. And here to here gives me P and, sorry, I dropped the J here, right? P and J. Right? And if you have taken your linear algebra well, and if you learn how matrix multiplication works, right? Matrix multiplication works as a dot product, right, of row and column, okay, to get to the entry of the product, right? So the ith row dot with a j column. And if you check, this is exactly the ith row. This is a j column. So this must result in the ij entry of the product, which is of course p and p here, so it's p squared. Okay, any question? So, right, even though trivial as in like, oh, it's so like natural, you don't even think about it. There's something sophisticated going on here, right? I want to say that probabilistically. First, there is a lateral probability conditional version. Then you drop the dependence on the not recent state to get you back to transition matrix. But once we get through all that, then you can see that, right, the n-step transition matrix is just the power, right, of transition matrix to the n, right, at the ij entry. Okay. So it's beautiful, right? The Markov property, and by the way, right, also note the time independence, time homogeneous is implicitly used here. So don't forget that, right? So it's not just Markov, it's also time homogeneity that ensure you get the same transition matrix at every time step. P. That's why it's p to the n, right? Or p to whatever the gap is, right? But so that, right? Yeah, right. So you can generalize to, if you want to go from I to j in n plus n steps, right? You can exactly just, you know, go from I to k in n step, and then k to j in m steps, like that for all possible k, or the other way around. You understand? So, right, if you want to go to from I to j in m plus n step, right? This is just start. It's just n. So notice, right? Because of time homogeneity, the s and t, the actual value doesn't matter. It's just a gap that matters. So that's m and n. And what we're showing you here is you can decompose it into possible ways. You can go from I to k in n steps, right? So the path from I to j, right? You can go from, you can break it like m like this, and then n steps, right? So you can go with all possible here and then there. Or you can break it to, sorry, this is s and this is t, right? ij. Or you can do n and then m, and then sum over all possibilities, like that. All right. Again, this kind of thinking, which is really, right, just connecting the path of a graph, will be important and relevant for some of our argument, right? So don't underestimate. Okay. Any question before we end today? Okay, very good. Then let's continue on Wednesday.
I actually have just one really quick question regarding the
Yep.
exam.
Uh-huh.
I wasn't sure if how like the points for the tests were going to be applied. Are those applied to the exam?
Points on what?
The extra points we got for doing the test, responders.
The equipment. The equipment check.
Yes.
Yeah, that one, again, right, is all under the group of midterm 1. So therefore, right, when it's tabulated, everything will be tabulated under midterm 1 group.
Okay, thank you. I just want to make sure.
Yeah, you can look at the grade, right? Yeah, to see.
Thank you so much, Professor. Have a nice day.
You too. Yep.
Thank you, Professor.
Yep. Thank you.
Thank you, Professor.